High voltage battery, Toyota Prius 2 training stand. Which contains a hybrid car, it has one of the components, a high voltage battery. This is a training stand, which displays all the main components of the high voltage battery. They are placed under safety glass and additional components, without which the high voltage battery would not function. These are the service plug with a fuse, 12-volt auxiliary battery, hybrid car's control computer, inverter, which includes a capacitor, other electronic components. But it is only for demonstrating how the system works and is controlled. What is under the acrylic glass is installed in the actual vehicle and normally not accessible. In this training stand, those parts are also not freely accessible and protected because they carry high voltage. Inside the battery, there are 1, 2, 3 connection relays. Pre-charge resistor for soft start. Current sensor. 4 battery modules are placed. The total number of modules can be checked. The remaining part here is drawn. For several reasons. If we placed all 28 modules, the stand would become very heavy and large. Such a stand is hard to carry from one classroom to another, and it takes up more space. Another thing, with real modules, the battery generates actual current and voltage. This stand is safe because we have the same voltage as the real stand, but we have a very, very low current, which ensures safety in the training stand. To represent and show how the middle of the battery is constructed, 4 modules are enough, and one module consists of 6 cells. If you look closely, you can see one part, 2, 3, 4, 5, 6, separated by stripes. These are cells, and one part is a module. The entire unit is a high-voltage battery. Battery's connection is made so that between modules 19 and 20, a service plug is inserted, exactly the same as in a real battery. When the service plug is removed, it disconnects the battery, disconnects the battery circuit, breaks it, and we exit. Here is the battery output, where we have 2 contacts, but no more voltage. The circuit is broken, and there is no more voltage. It's important to note that in the Toyota Prius 2 battery, the service plug does not divide the battery into 2 equal parts. It splits it into uneven sections. In one section, we have 19 modules, and in the other from module 20 to module 28. And these sections, when the service plug is removed, have different voltage levels. Next, under the cover there is, just like in the actual battery, a service current sensor, which in this case has no function other than to show what's inside. Also under this cover, in the real vehicle is installed the battery management computer, which communicates with the hybrid vehicle's control computer via the CAN bus. Continuing about the stand, we have 2 separate terminals brought out externally for educational purposes. So we can demonstrate that when the service plug is removed, the internal battery circuit is disconnected. Through these terminals, we can measure the high voltage battery's voltage, and the nearby LED shows that the service plug is inserted. On the other side, we have measurement terminals that mostly represent the work of the relays, when the hybrid car's control computer activates those relays in a certain sequence, and then from the high voltage battery voltage is delivered to the inverter. So on these terminals, we can see voltage when the relays are activated. The conditions for activating the relays are also specific. That is, the ready mode must be turned on. By pressing the power button, the ready mode activates just like in a real vehicle, and the instrument panel shows the ready indication. The inverter cover must be properly closed, and to simulate proper cover closure, this jumper is used. Basically, if we remove it, we simulate that the cover is incorrectly closed. The signal from that sensor switch goes to the hybrid system computer, and if the inverter's signal is incorrect, the LED does not light up, and the stand or the hybrid system control computer will not activate the relays. Another jumper is used to simulate or disconnect the 12-volt battery. According to the requirements, to remove the service plug, we must first turn off the ready mode in the vehicle and wait 2 minutes. Then, disconnect the 12-volt battery terminal. So by removing this jumper, we simulate that the 12-volt battery terminals are being disconnected. And when the switch is turned off and the jumper is pulled, after 2 minutes, the service plug can be removed. It can be powered from a household electrical outlet, or it can be powered using an external 12-volt battery, which we simply place next to the stand and connect to these terminals. The positive from the battery to the red terminal, and the negative from the battery to the black terminal. When you connect the 12-volt battery, this LED stays lit. And when working further with the stand, there's no need to disconnect the battery. Terminal disconnection is simulated by removing this jumper. It demonstrates how the stand works when connected to a power source. We plug it into an outlet. Here we have a switch which, when turned on, powers the stand. This LED indicates, or shows, that we have 12-volt power, meaning our battery is connected and powering the stand. So, the stand can be powered from either an external 12-volt battery or a laboratory power supply set to 12 volts, or simply from a standard wall socket. Now, this LED indicates that the hybrid system or hybrid vehicle control computer is receiving power from the battery. If I now take and remove the jumper, you see the 12-volt battery is connected and working, but the hybrid system control computer no longer has power. So removing this jumper simulates disconnecting the negative terminal of the 12-volt battery, because by regulations, the negative terminal must be disconnected before performing further actions. This LED indicates that the so-called interlock is enabled properly, meaning the cover is closed correctly. The jumper is inserted, and the service plug is also connected or properly latched. If I now remove the service plug, I open the interlock. The circuit is open, and this LED turns off. This is a signal to the hybrid system control computer that we cannot activate these relays. Furthermore, if the inverter cover is closed incorrectly, we also get a signal that something is incorrect. And the hybrid system computer will not activate the relays. Also, when removing jumpers here or opening the service plug, a sound is heard. This sound in the stand is made so that when students are working, they are notified by sound that they are doing something incorrectly or out of the order prescribed by the manufacturer, because there is a specific order for how the service plug must be removed or the hybrid system turned off. This switch is equivalent to when you sit in the car and press the start button or start the vehicle. Note that when you press this button, the ready light turns on. This is equivalent to the ready message that appears on the instrument cluster. And now I press it. All relays, everything is connected. This LED started glowing, indicating that the system is now ready, as if for driving. The vehicle is ready to drive. The real LEDs indicate which relays are currently activated, and their activation sequence also corresponds to the manufacturer's setup. One relay is activated, the circuit is checked, then it's turned off. The next relay is turned on. Then the first relay is reactivated. Finally, the third is switched on, and the second one is turned off. This whole sequence can be observed through the LEDs as they blink. But this happens rather quickly, and noticing it with the naked eye is quite difficult, which is why we have an additional switch here. With this switch, we can reduce the relay activation speed by turning the switch, essentially slowing it down. The whole activation process then happens 10 times slower. I will demonstrate this now by turning it off. And now if I pay attention to the LEDs, we can see how it happens at normal speed. Now let's reduce the activation speed by 10 times and observe how the relays activate more slowly. This is done to understand the sequence, why one relay is switched on first, then the next, and so on. This is done to check the circuit for any current leakage, damaged cables, and so on. In the same way, it switches off slowly when the switch is set to 10 times slower speed. Next, we turn on the vehicle. When the relays are connected, we see this LED light up. This indicates that high voltage from the battery is going to the inverter. We can actually measure the voltage at these contacts and check it. Now I will switch off the vehicle and pay attention to the fact that one LED goes off immediately while the other stays on, and it stays on for 5 to 10 minutes. Because inside the inverter, there's a capacitor with a capacitance marked here, and the capacitor slowly discharges, and the LED remains on for as long as there is voltage in the capacitor. This is real time with real voltage, just as it would be in an inverter capacitor. Now I will further explain about the contacts. Measurement contacts, which are not present in a real car, but in this setup, they are added specifically to demonstrate battery voltage and to demonstrate, explain, and show what effect removing the service key has. High voltage measurement. DC 1000 volts. And in this case, measurements should be done using protective gloves. Since we're dealing with high voltage, safety measures must be used. We have 215 volts of DC voltage. So, this shows what is inside the battery when the service key is inserted. Now, we'll show how high voltage appears outside the battery when the relays are connected and voltage appears even when the soft start relay is activated, because current still flows through it. We have an illuminated LED, which informs us that the stand is on and voltage from the battery is traveling through wires to the inverter. Now I turn the stand off. Voltage from the battery is cut, but voltage in the inverter, you see, it's not here. But in the inverter, the voltage is still present and gradually drops. Since the capacitor has a certain discharge time, voltage gradually decreases, and over about 10 minutes, it will discharge to 0. Now we have 12-volt voltage. Set the multimeter to the 20-volt measurement range. This first relay will be on for a very short time. Because it's for checking, it will quickly turn off. But try it. Voltage appeared and then turned off. We're actually measuring the control voltage of the relays. In this case, the relays are controlled by a positive signal. Voltage is applied to the relay for it to activate. The third one also activated, the signal is received. If we turn off the stand, voltage is cut, and the relays close, or open, to disconnect the circuit. We send this. Then remember that the time will be 10 times longer. We also have battery power supply here. Or we can also measure the battery voltage here. If we don't have household electric power, we can use a 12-volt battery or a lab power supply set to 12 volts. Now the procedure for properly removing the service key, the requirements are as follows. First, we must turn off the car by pressing until the ready indicator goes off. Press the button and the relays must turn off. Ready mode has turned off. Then, we must wait 2 minutes. During those 2 minutes, we can prepare safety equipment, gloves, voltage tester, and all the other. We put on the safety glasses and check the gloves. The gloves must be certified and have a metrological inspection. Glove inspection is done like this. Air is blown inside and the end is sealed tightly. Then by pressing, we check if there are any tears where air could freely escape. This is how we check gloves. The second glove is checked the same way. Blow air in, squeeze, and check for any torn areas where air would escape easily. After 2 minutes have passed, when the ready mode is turned off, we disconnect the battery's negative terminal by pulling out from the battery clamp. And then after a few minutes, we can remove the service key. First, we have to lift the service key. This unlocks and breaks the interlock circuit here. Then we tilt the key downward while pulling it out completely. And that's how the service key is removed. The service key, according to requirements, must be kept in your pocket or placed in a safe place so no one passing by would decide to put it back in. In this case, the service key is best stored in a special box, or somewhere where no one passing by can access it, take it, or insert it back again. Once the service key is removed and placed safely, we need to wait 10 minutes until the capacitor in the inverter is fully discharged. The LED must turn off completely. Only then can we continue working on the stand or on the car. We should measure again if there really is no high voltage anywhere. And if there isn't, we disconnect wires from the vehicle or begin repairing some high voltage components, such as the drive motor or the AC compressor motor. After disconnecting wires, we must insulate them. Inside the service key, there is a fuse. To access it, you have to disassemble everything here. But we can check the fuse to see if it's good simply by measuring voltage and checking continuity between these two main contacts. These are the main power contacts, and these are two smaller contacts called interlock. The interlock contacts are here on the side. When we lock the service key and press it down, this section connects with this part. The main power contacts are here. Now, I want to demonstrate what effect the key has and when it affects high voltage inside the battery. I set the measurement voltage to 1000 volts. We see that it's lit. The LED shows that these contacts are connected properly, and we can monitor it slowly. I lift the key, interrupt the interlock circuit, but the battery hasn't yet been split into two parts. I begin turning the key downward, push the lever down, and slowly begin pulling out the contacts, and right at this moment, when the LED goes out and you see the voltage disappears, that's the moment when the main power contacts in the service key disconnect. In this case, the voltage in the closed battery circuit is gone. Therefore, if for any reason the relays are faulty, if they failed or welded and didn't disconnect, we would not have voltage on these contacts. I'll try to insert the service key back in and watch when the LED lights up. At that moment, the circuit connected. Look, the circuit has already connected even though I haven't yet fully inserted the service key or locked the lever, connected the interlock, and locked the latch. Once the service key is removed and placed safely, we need to wait 10 minutes until the capacitor in the inverter is completely discharged. The LED must turn off completely. Only then can we continue working on the stand or the vehicle. We should measure again whether there is truly no high voltage. If there isn't, then we disconnect some wires from the car or begin repairing some high voltage components, like the drive motor or the AC compressor motor. After disconnecting wires, they must be insulated. To check the service key, whether the fuse is not blown, can be done in a simple way. We just set the multimeter to continuity check mode. If there's a beeping sound, it means the circuit is closed. Touch the probes to the contacts. If there is an audible signal, it means the fuse is not blown, and the connections between these contacts and the fuse are good. You can also measure resistance, which should be less than 1 ohm, as declared by the manufacturer. We also set it to measure resistance, touch the contacts, and the resistance should be less than 1 ohm. This is how we check the main power contacts. In the same way, we can check the interlock too. Interlock circuits. The resistance must also be less than 1 ohm. 0.7 is acceptable. You can also check using circuit continuity, or simply with the beeping signal. That can also be used for checking. This means both circuits are in working order. This is a no-load test, but it still works. If we have a vehicle that is turned on, and we do something incorrectly, then this stand reacts just like a real vehicle. For example, I'll now try to improperly, against the rules, remove the service key, pull out the fuse, and watch how the control unit reacts, which automatically shuts off the relays, and the voltage coming from the high-voltage battery is instantly disconnected. If a person begins to act incorrectly, the system reacts and disconnects the car. Now, you heard the audible signal. It will always be present when doing something against the rules. In this case, we need to activate the ready mode and try to open the inverter cover. It alerts us that we did something wrong against the rules. If I try to open the service key, it also alerts. We're not in ready mode, but we still have power in the hybrid system control computer. It also alerts that we're doing something incorrect. I also want to demonstrate how to measure the voltage remaining inside the battery when the service key is removed. In this case, I choose the positive terminal. I trace where the wire goes. There, it only passes through a small part and reaches the upper contact. Here, I connected the upper contact to negative and have the red positive on top. In this area, where there is a smaller number of modules, the voltage here reaches about 60 volts. If you want to measure the voltage across a larger part of the battery, I choose to connect the negative terminal here. I follow the wires. They go through a larger section, drop down, go through this module. The circuit connects here, returns, and that means I need to connect to the bottom contact on the service key. Here, I get around 150 volts of direct current. These voltages may vary depending on how much charge the battery modules have, how charged they are. So the voltage may vary. The nominal calculated full battery voltage is 201.6 volts. But if the batteries are more charged, the voltage will be higher, and if they're more discharged, the voltage will be lower. The stand is designed to allow you to measure individual module voltage separately. Each module's voltage can be measured separately. For that, 20 volts is sufficient. And the module voltage can be measured separately by observing where the terminals are. The positive terminal is visible on the battery, and the negative. I connected the contacts like this, and we have the voltage of one module. We can measure the next one again. 7.4 volts. We can measure the third and fourth as well, but then we need to change the multimeter, or evaluate that it will show a minus sign due to polarity. We won't change that by swapping multimeter probes. This way, the voltage of each module can be measured. In a real battery, this wouldn't be possible, because you would need to disassemble the battery, but here, it can be done through the prepared contact holes.